see the effect of horizontal acceleration for reservoir full condition and for reservoir empty condition. So I think under this seismic horizontal acceleration, we should understand inertia, which is the resistance to the direction of motion. So let us see, for reservoir full condition, the worst case is just when the earthquake acceleration moves towards the upstream direction, then inertia force will be to the downstream direction. As a result, the corresponding inertia may act to downstream, then the dam may slide. So this is the worst case for reservoir full condition. So inertia may be to the upstream direction, then earthquake acceleration may be to the upstream direction, then inertia will be to the downstream direction. So that is the worst case. For reservoir empty condition, just the reverse. The worst case occurs when the earthquake acceleration moves towards the downstream direction, then the inertia force will be to the upstream direction. As a result, the dam may collapse. So I think you can see now, this is the equation for a horizontal inertia force, which is derived from Newton's second law. Force inertia horizontal equal to mass times acceleration. Mass means just W over G. Then earthquake acceleration means alpha H seismic coefficient times acceleration due to gravity, which is G cancel, then alpha H times W. So I think we can see this formula. Then you can distribute to the free body diagram. Now let us see horizontal acceleration or alpha H, which is hydrodynamic pressure actually, just exerted on the dam structure. So let us see. Horizontal acceleration may be to the upstream or to the downstream direction. So you have just disturbance on the water body. So earthquake acceleration, which is force of earthquake to the downstream direction, which is acting to the dam structure. So you have seen. So I think when earthquake acceleration is to the upstream direction, which is alpha H times G, then inertia force will be to the downstream direction. Now let us see. So this is according to Van Korman equation. So this is just parabolic distribution. It acts at 4h over 3 pi from the base of the dam. So this is horizontally, it may act. Now on the body of the structure, also shocking effect. So just you have W1, W2, then when earthquake acceleration moves to the upstream direction, then inertia force will be to the downstream direction. So then you will decompose. So W1 will be W1 EH to the downstream direction, W2 EH like that. So this is just alpha H times W1 and also W2 EH alpha H times W3. If you have W3, similarly alpha H times W3. So this is just also a hydrodynamic formula developed by Zanger, but for an average ordinary purpose, Van Korman equation is sufficient. So let us see effect of vertical acceleration. So when the reservoir is full condition, so if earthquake acceleration acts downward, then inertia will be to the upward direction. As a result, it adds to the uplift pressure, then the dam may overturn. So just the effective weight of the dam and water decreases. As a result, stability will decrease. So this is the equation for effective weight of the dam, W prime, which is W original weight, then 1 minus alpha V. So as a remark, vertical acceleration does not alter the volume of concrete and also water in the reservoir. It doesn't alter. If the vertical acceleration acts in upward direction, inertia will be the downward direction. So as a result, this may just stability increase. Effective weight of the dam in water increases. As a result, the stability may increase. So effective weight will be just W times 1 plus alpha V. So these are just seismic coefficient horizontal earthquake acceleration classification. So you may have zone 0, which is alpha H 0, nil, no general damage. just 1 minor, then it go up to 4, which is great, just general damage level. So let us see. So the values of alpha h and alpha v are generally expressed as a percentage of acceleration due to gravity. It could be 0.1 g or 0.2 g, etc. So the worst case is just when earthquake acceleration is to the downward direction, then inertia force will be to the upward direction. So as a result, the dam may fail. So this is the direction of upward vertical acceleration. Then inertia force will be to the downward direction. Then I think this may just, you can see the base contact between foundation and dam will increase. Then the effective weight of the dam will also increase. So this is important. So the worst case is just when acceleration is downward, inertia will be to upward. So W1 EV and WT EV to the upward direction. So this is important. So contact between just when earthquake acceleration is to the upward direction, it will increase. You can see like this. So the contact between dam and foundation, if it is just downward acceleration, then you have upward. So this is just worst case. You can see. So if acceleration is downward, inertia will be to upward direction. If it is reverse, then the contact will increase. So effective weight will decrease. So this is just hydrodynamic force on body of water. So we will have formulas on the body of water. So according to Westergaard, relative to any elevation at depth z below water surface, the pressure or the earthquake pressure of water will be this equation, Ce alpha h gamma w times z max. So z max is maximum depth of water at the section of the dam. Consider at any section, you can consider, then above that you can calculate the hydrodynamic pressure force, which is at any depth of water below water surface at any z. So C is the dimensionless pressure factor, z over z max and phi upstream. You have a table with respect to z and z max and phi upstream. Phi upstream is inclination of upstream slope with a vertical. Then you have CE, dimensionless pressure factor. Then you will substitute in the equation. Then you can find the pressure, hydrodynamic force. So total hydrodynamic load is given by this equation, total hydrodynamic load. So this is the pressure, and total hydrodynamic load will be this equation. So it acts at 0.48 above any section XX considered. Okay, according to Van Korman equation, I think hydrodynamic pressure has parabolic distribution. So you can find earthquake force, which is horizontal at 4h over 3 pi from the base. But according to the Zanger method, the intensity of hydrodynamic pressure at a depth y below water surface could be given by this equation. You can see this equation, C times alpha h gamma w h. H is head water depth, Cm is this is a dimensionless factor with respect to phi upstream. Then you can calculate. Then once C you calculate, then you have Cm. Then phi upstream also known. Then you can find total intensity of hydrodynamic pressure at any depth y below water surface. So the pressure force will be this one. So I think this is important. So load combinations, you have 3 load combinations: normal load combination, unusual, and exceptional. So you can do accordingly. So normal load combination, self-weight, water pressure at normal maximum level, tailwater level at tailwater level, drains, functional, ice, silt, etc. Unusual load combination is just you will add silt pressure, and also drain inoperative, and also water pressure at design flood level, and tailwater at minimum. But exceptional load combination, you will add seismic load or earthquake force. So you can see now draining operative, silt, and seismic load. Okay, this is a sample free body diagram for overall load combination, which is normal, unusual, and exceptional load combination. You can see earthquake. If you have earthquake, then you have parabolic distribution, which is in addition to hydrostatic pressure, you have disturbance on the body of water, shocking effect. So on the structure also you have W1AH, W2, W3, etc. So I uplift the rest as usual. So this is gravity dam design and analyze. So the three conditions for structural equilibrium, just to make stable, you have sigma h 0, sigma v 0, and sigma m 0. So summation of this must be 0 at any point. So the profile must have sufficient safety factor with respect to rotation and overturning, which is F naught, translation and sliding, which is FSS, overstress and material failure, which is related to shear. So you have overturning stability, factor of safety against overturning F naught in terms of moment about the downstream toe of the dam. You have F naught overturning stability, summation of moment positive divided by summation of moment negative. So if you get more than 1.25, it may be acceptable, but more than 1.5 is desirable or safe. So you can see. So this is just the resisting moment and driving moment. So if it is clockwise moment, it is a driving moment. But if it is counterclockwise moment, which is a resisting moment, we will see. Sliding stability, just factor of safety against sliding for horizontal foundation. You have this equation, mu times sigma h over sigma v, where mu is just coefficient of sliding factor, coefficient of friction, sliding friction, and also this equation for alpha more than 0 if it is inclined to some degree. So the next one is shear friction factor, just S over sigma h. S is the resistance to sliding and shear and total horizontal force. So for alpha 0, it looks like this horizontal foundation. But for alpha more than 0 inclined foundation, you get S this one. For horizontal foundation, you get this equation. So in either equation, you can use it accordingly. So this is sometimes you may just include downstream passive wedge resistance, which is a further component to resistance and sliding, which can be mobilized. So this is downstream wedge resistance sometimes. So you have this dam. So this dam may just slide to this under shear, but this is a resistance, which is PP. So you can find this equation, just RW resistance to sliding and resistance of the wedge against sliding to this direction. So you have weight of wedge, passive wedge, then PP, passive wedge resistance. You can use this equation where WW is weight of the wedge and AAV is area of this component, area of inclined face. Then you can use this equation weight of the wedge, which is gamma of the wedge times area. So shear friction, just S plus PP. You can add PP, passive wedge resistance, if you have wedge resistance. Then finally, this result must be more than or equal to 3. Okay, limit equilibrium, I think you know this equation, shear stress over shear strength. So shear stress over shear strength over shear stress. Shear strength, you know this equation from solid mechanics, more column circle, which is more Taylor criterion. Can use this equation. So for horizontal inclination, this one, and for inclined foundation, this one. So stress analysis in gravity dam, the stress evaluated in a comprehensive analysis are just comprehensive analysis are vertical normal stress, sigma z on horizontal plane, horizontal and vertical shear stress to zy and to yz, and also horizontal normal stress on vertical planes, and principal stress sigma 1 and sigma 3, direction and magnitude. So if you see, this is a 3-dimensional axis of gravity dam. So sometimes you can just see whether you calculate sigma z, sigma y, and to zy, yz, etc. So the vertical stress is just this one for reservoir full condition. This formula is derived from this one, from this equation, which is from modified beam theory, just by combining axial load and bending load. Axial and bending load. So I is second moment of inertia. Then you can include. Then finally, you will find this equation for reservoir full condition. But for empty condition, let us see. where E is eccentricity of the resultant load R, which must intersect the plane downstream of its centroid for reservoir full condition. So excluding uplift moment and uplift force, you can use this equation for centroid. Then finally eccentricity. So eccentricity is T over 2 minus X bar. So once you find eccentricity most of the time, if it is more than T over 6, 1/6 of the base dimension, then you have the vertical stress is negative, which means tensile stress is developed on the upstream face of the dam. So just eccentricity should be less than T over 6. Just the resultant should pass within 1/3 of the base contact. Horizontal and vertical shear stress, you can use this equation. Just this equation where phi upstream and phi downstream, upstream inclination from vertical line and downstream inclination from horizontal line. So these are horizontal normal stress sigma y. So sigma y PW, which is water pressure, which is gamma W times Z1 sigma Z upstream, then PW times square phi upstream. This is horizontal normal stress sigma YD. Also, you can use this equation. So finally, principal stress for upstream phase, you can use this equation, and this is minor principal stress in the upstream. For downstream, this one, and for minor major principal stress upstream and downstream. This is downstream. This is also downstream minor principal stress. That's how you can. Principal stress also just you can have this triangular portion, then stress distribution, then you can just see the resultant once you just do this one, then you can find the above equations. So resultant force equation for reservoir full condition, most of the time this resultant are to the downstream of the centroid, but for reservoir empty condition to the left, to the upstream direction. Okay, permissible stress and cracking, just horizontal cracking assumed to occur if sigma Z minimum without uplift below limit set by this equation. So if you get this equation, then you can find the minimum normal stress at the upstream side. So where Ft is tensile bond strength of concrete, and Kd is just if drain effective 0.4, otherwise 1. So this is just base dimension you can find. So factor of safety Ft, 3 for normal load combination, 2 for unusual load combination, and 1 for exceptional load combination. Okay, design gravity dam profile. I think we will proceed in the next slide. And thanks for watching this video. So this is all about today's lecture. Hopefully you liked the video. If you have any comment or question regarding this topic, please write down in the comment section below. I will reply on it. Please like, share, and subscribe this video to get more precise lectures. Thanks.